In this video, I will be discussing about how to compute the sample mean vector and the sample covariance matrix. Now, suppose you want to study more than 2 variables, say for example, 3 or more variables. It is very convenient if you apply the knowledge of linear algebra in the computation of the descriptive statistics of these variables. In other words, applying the concept of matrices will facilitate in the computation of the descriptive statistics for these variables. For example, you want to study variable x sub 1 and another variable, say variable x sub 2, and then variable x sub 3, and so on and so forth until you will reach to the last variable that you want to study, say p variable, and obtaining n observations for these variables. So you have n observation here. So the first data element is the data point x sub 1, 1, meaning this is the first observation for the first variable. We have x 2, 1, meaning the second observation for the first variable. We have also x sub 3, 1, the third observation for the first variable, and so on and so forth. You will reach to the last observation n for this first variable. And also for the second variable, you will have x sub 1, 2, because this is the first observation for variable 2. We have x sub 2, 2, the second observation for the second variable, x sub 3, 2, the third observation for the second variable, and so on and so forth until you will reach the n observation for the second variable. Now let's go for the third variable. We have x sub 1, 3, the first observation for the third variable. We have x sub 2, 3, the second observation for the third variable. And we have x sub 3, 3, the third observation for the third variable, and so on and so forth until you will reach the n observation for the third variable. And until you will reach to the last variable that you want to study. So this is the first observation for the p variable, the second observation of the pth variable, the third observation for the pth variable, and so on and so forth until you will reach the last element, the last data point, the n observation for the pth variable. So this is our matrix organizing all the data elements in our study. Now, take note that we are studying here p number of variables, p variables here, and there are n observations. So n observations here, where I is from 1 to n, because there are n observations here. And your j is from 1 to p, because there are p variables here. So when you speak of a data point of x sub ij, it means that this is the ith observation on the jth variable. Now let's apply this concept in a real example here. Suppose we are studying 3 variables here. So this is our x sub 1 variable, x sub 2 variable, and x sub 3 variable. So there are 3 variables here, and there are 6 observations. So 1, 2, 3, 4, 5, and 6 here. And so to solve for the means of these 3 variables, let's compute for the sample mean vector. And the sample mean vector is equal to 1 over n times x transpose, the transpose of this matrix, and the matrix J, where x is the data matrix whose elements are real numbers of size n by p, because there are n observations here, n rows, and p columns, the number of variables. And we have also the matrix J, whose elements are real numbers of size n by 1. So therefore we can solve for the transpose of this matrix. So this is matrix X transpose, and the transpose of the matrix is writing the first column as the first row of this matrix. So we have 5, 24, 15, 10, 5, and 25. Also, the second column becomes the second row here. So we have 80, 89, 85, 84, 82, and 90 here. Also, the third column becomes the third row, which are 50, 30, 25, 11, 45, and 7 here. So this is the transpose of this matrix, and we write it here, X transpose. And then we will construct for the matrix J. The matrix J is a vector wherein the elements are all 1, and the number of ones depends on the number of observations here. And because there are 6 observations, we have 6 ones here. So this is of size 6 by 1, but our transpose is of size 3 by 6. Thus, to compute our sample mean vector, which is equal to 1 over n times X transpose J, we have 1 over 6, because there are 6 observations here, times the transpose of X, which is this one. So we just copy this one here, 5, 24, 15, 10, 5, 25. And then we have the second row, 80, 89, 85, 84, 82, and 90. And the last row is 50, 30, 25, 11, 45, and 7. So this is our X transpose. But this is multiplied by the matrix J. So we write here the matrix J with 6 ones here. And this is equal to 1, 6 times the product of these two matrices, 5 times 1, which is 5, added to 24 times 1, which is 24, 15 times 1, so that is 15, added to 10 times 1, so we have 10, and then 5 times 1, we have 5, and then 25 times 1, which is 25. Also, we multiply the second row with this column here. So we have 80 plus 89, 85 times 1, we have 85, and then 84 plus 82, and then 90. Also, we multiply the third column by this vector here of whose elements are 1. So we have 50 plus 30 plus 25 plus 11 plus 45 plus 7 here. So this is our product of these two matrices. So we have the sample mean vector is equal to 1 over 6 times a vector whose elements are the sums here. So we have the sum of these 6 numbers, which is 84. And then the sum of the second row is 510. And then the sum of the third row is equal to 168 here. And if we multiply that one by 1, 6, because this is a scalar multiple of this matrix, we have a vector which is having elements of 14, 85, and 28. So this is now our sample mean vector. Hence, we conclude that the mean of our first variable is equal to 14. And the mean of the second variable is equal to 85. And also the mean of the third variable is 28 here. Now let's proceed to computing the sample covariance matrix for this data matrix here. And the covariance matrix, which is represented as the covariance of every pair here. So x sub j and x sub k is equal to 1 over n minus 1, because we consider this one as a sample of all the target population, then we multiply this one by X transpose times the identity matrix I minus 1 over n of the matrix J times the data matrix X, where this matrix of I minus 1 over nj is a matrix whose elements are real numbers of size n by n. So matrix I is an identity matrix of size n by n, but this matrix J is a square matrix whose elements are all ones. So we define here that J is a square matrix whose elements are all ones. So elements are real numbers of size n by n because that's a square matrix. So computing for this covariance matrix, this is equal to 1 over 6 minus 1 because there are 6 observations here. And this is multiplied by the transpose of the matrix X times this I. And we know that I is an identity matrix whose elements in the main diagonals are all ones, but all the rest are zeros. So we have here 0, 1, 0, 0, 0, 0, and this is 0, 0, 1, 0, 0, 0, and 0, 0, 0, 1, 0, 0. And we have here 0, 0, 0, 0, 1, 0. And we have the last row of zeros except the last element here, which is 1. So this is our identity matrix I. And then we subtract here the scalar multiple of our J matrix, whose elements are all ones. So 1, 1, 1, 1, 1. So there are 6 ones in the first row, and also 6 ones in the second row, 6 ones in the third row, 6 ones in the fourth row, and ones also in the fifth row, and in the last row are all ones there. And then we multiply this one by the data matrix X. So this is equal to 1/5 of the X transpose of this matrix, the identity matrix here, which is 1, 0, 0, 0, 0, and 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, and 0, 0, 0, 1, 0, and 0, 0, 0, 1, 0, and we have the last one, which are all zeros, but with a 1 in the last element. And this will be subtracted by this scalar multiple of this matrix by multiplying 1/6 here. So this is 1/6 because 1/6 times 1, that's 1/6. So 1/6, 1/6, 1/6, 1/6, 1/6 here. So there are 6 1/6, and also 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. Also in the third row, all are 1/6 because the ones will be multiplied by 1/6, all of them. And then also the fourth row will multiply it by 1/6. And the fifth row are all 1/6. Also the last row is also 1/6. And this is multiplied by the data matrix X here. So this covariance, we can represent this one as the sample covariance matrix S. So the sample covariance matrix, which is S, is equal to the 1/5 of the data matrix transpose times the difference of these two matrices. So 1 minus 1/6, that's 5/6. And then 0 minus 1/6, that is negative 1/6. So all of these are negative 1/6 here, because zeros, when subtracted by 1/6, the difference is negative 1/6. So we have here also negative 1/6, because that's 0 minus 1/6, so negative 1/6, but 1 minus 1/6, that is 5/6. So this is also negative 1/6, all of them in this row. And also the third row, 0 minus 1/6, that's negative 1/6. Negative 1/6, but the third element is 5/6, because that is 1 minus 1/6. So that is positive 5/6, and all the rest are negative 1/6 here. Also 0 minus 1/6, so this is negative 1/6, negative 1/6, negative 1/6, but this is 5/6, because 1 minus 1/6 is positive 5/6, and the last two are all negative 1/6. Also, we have here negative 1/6, negative 1/6, negative 1/6, negative 1/6, but this is positive 5/6, and the last one is negative 1/6. And then for the last row, we have negative 1/6, negative 1/6, negative 1/6, negative 1/6. Also this one, negative 1/6, because we have here 5 zeros. When subtracted by 1/6, the difference are all negative 1/6, but the last one is positive 5/6, because this is 1 minus 1/6, and the difference is positive 5/6. And then we multiply this one by the matrix, by the data matrix X, which is this one. So we have 5, 24, 15, 10, 5, and then we have here 25. So this is the first variable, and the second variable is 80, 89, 85, 84, 82, and 90. And then the last, which is the third variable, is 50, 30, 25, 11, 45, and 7. So this is our data matrix X. So to separate our solution from example 1, we will make a border here. So for our covariance matrix S, we have this 1/5 of the data matrix X transpose multiplied by the product of these two matrices. And how do we multiply? We multiply the first row by the first column. So 5, 6 times 5, that's 25 over 6. And then minus 24 over 6, minus 15 over 6, minus 10 over 6, minus 5 over 6, and minus 25 over 6. And if you add those 6 numbers, we have a sum of negative 54 over 6 here. And then we also multiply the second row by the first column to obtain our second element in the first column of our product. So we have negative 1/6 times 5, that is negative 5/6. 5/6 times 24, that is 120 over 6. And then we have negative 1/6 times 15, that is negative 15 over 6. Negative 1/6 times 10, that is negative 10 over 6. Plus the negative 5 over 6 minus 25 over 6. So adding the 5 products here, we have 60 over 6. Also multiplying the third row by the first column to obtain the third element here. So we have negative 5/6. If you multiply negative 1/6 by 5, added to negative 1/6 times 24, which is negative 24 over 6, added to 5/6 times 15, which is 75 over 6, minus 10 over 6, minus 5/6, minus 25 over 6. So if you add the 6 products here, it will give you a sum of 6 over 6. And then multiplying the fourth row by the first column also. So negative 5/6 minus 24 over 6, minus 15 over 6, and then plus 50 over 6 because that is 5, 6 times 10. So that is 50 over 6 minus 5, 6 minus 25 over 6. And the sum of the 6 products here, we have negative 24 over 6. Also, the 5th row multiplied by the first column. So negative 5, 6 plus the negative 24 over 6 plus the negative 15 over 6 plus the negative 10 over 6 and plus 25 over 6 and then minus 25 over 6. And adding the 6 products, it will give you negative 54 over 6 here. And lastly, multiplying the last row by the first column, we have negative 5, 6 plus negative 24 over 6 plus negative 15 over 6 plus the negative 10 over 6 plus the negative 5 over 6 plus 5 times 25, it's 125. So that is 125 over 6. And then adding those 6 products, we have 66 over 6. So this is the first column of our product matrix. Now, the next is to multiply the first row by the second column here. So we have 5, 6 times 80, we have 400 over 6, minus 89 over 6, minus 85 over 6, minus 84 over 6, minus 82 over 6, and minus 90 over 6. And the sum of those 6 products is equal to negative 30 over 6. Now, multiplying the second row by the second column also, we have negative 80 over 6 added to the product of 5, 6, and 89, which is 445 over 6, and then minus 85 over 6, minus 84 over 6, minus 82 over 6, minus 90 over 6, and the sum of these 6 products is equal to 24 over 6 here. Now, multiplying the third row by the second column, so we have negative 80 over 6 minus 89 over 6 added to 5, 6 times 85, which is 425 over 6, and then added to negative 84 over 6 minus 82 over 6 minus 90 over 6. And adding those 6 products, we have 0 over 6 here. Now, multiplying the fourth row by the second column, so we have negative 80 over 6 minus 89 over 6 minus 85 over 6, and then added to 5, 6 times 84, which is 420 over 6 minus 82 over 6 minus 90 over 6. And adding those 6 products, we have negative 6 over 6 here. And the fifth row, multiplying by the second row, we have negative 80 over 6 minus 89 over 6 minus 85 over 6 minus 84 over 6 added to the product of 5, 6 times 82, which is 410 over 6, and subtracted by 90 over 6. So adding those 6 products, we have negative 18 over 6 here. And lastly, we multiply the last row by the second column. So we have negative 80 over 6 minus 89 over 6 minus 85 over 6 minus 84 over 6 minus 82 over 6, and added to the product of 5, 6, and 90, which is 450 over 6. And combining all the 6 products there, we have 30 over 6. And then again, we multiply the 6 rows by the last column here. So we have 5, 6 times 50, which is 250 over 6, minus 30 over 6, minus 25 over 6, minus 11 over 6, minus 45 over 6, minus 7 over 6. And combining the 6 products, we have here 132 over 6 here. And then the second row multiplied by the last column, we have negative 50 over 6, and then added to 5, 6 times 30, which is 150 over 6, minus 25 over 6, minus 11 over 6, minus 45 over 6, and minus 7 over 6. And combining all the 6 products there, we have 12 over 6 here. And then multiplying the third row by the last column here, minus 50 over 6, minus 30 over 6, added to 5, 6 times 25, which is 125 over 6, minus 11 over 6, minus 45 over 6, minus 7 over 6. And combining the 6 products, we have here negative 18 over 6. Then the fourth row is multiplied by the third column. So we have negative 50 over 6, minus 30 over 6, minus 25 over 6, and then added to the product of 5, 6, and 11, which is 55 over 6, minus 45 over 6, minus 7 over 6. And the sum of the 6 products is equal to negative 102 over 6 here. And then multiplying the second to the last row to the third column, we have negative 50 over 6, minus 30 over 6, minus 25 over 6, minus 11 over 6, and then 5, 6 times 45 is equal to 225 over 6, minus 7 over 6. And combining all the 6 products there, we have 102 over 6 here. And the last row multiplied by the third column, we have negative 50 over 6, minus 30 over 6, minus 25 over 6, minus 11 over 6, minus 45 over 6, plus the product of 5, 6, and 7, which is 35 over 6. And the result is equal to negative 126 over 6. And this is the product matrix of these 2 matrices. So this is equal to 1/5 times the transpose matrix of the matrix X, which is this one. So that is 1/5 of 5, 24, 15, 10, 5, and 25. And this is 80, 89, 85, 84, 82, and 90 here. We have also 50, 30, 25, 11, 45, and 7. And this is multiplied by this matrix here. And this matrix, if we want to simplify, negative 54 over 6 is negative 9. 60 over 6 is 10. And 6 over 6, which is this one, is 1. And then negative 24 over 6, which is negative 4. And negative 54 over 6, which is negative 9. And then 66 over 6, which is positive 11. And then negative 30 over 6, which is negative 5. And then 24 over 6, which is 4, 0 over 6 is 0, negative 6 over 6 is negative 1, negative 18 over 6 is negative 3, and 30 over 6 is 5. And then 132 over 6 is 22, and 12 over 6 is positive 2, negative 18 over 6 is negative 3, and negative 102 over 6 is negative 17, and 102 over 6 is positive 17, and negative 126 over 6 is negative 21. So this is our simplified form of this matrix. So our sample covariance matrix is equal to 1/5 of the product of these 2 matrices here. So we have 5 times negative 9, which is negative 45, added to 24 times 10, which is 240, and then 15 times 1, which is 15, and we have 10 times negative 4, which is negative 40, and then 5 times negative 9, which is negative 45, added to 25 times 11, which is 275. And then multiplying also the second row by the first column. So we have 80 times negative 9, we have negative 720. And then 89 times 10, which is 890. So plus 890. And then 85 times 1, we have 85. 84 times negative 4, which is negative 336. And then 82 times negative 9, we have negative 738. And also 90 times 11, we have positive 990 here. And then multiplying the third row by the first column, we have 50 times negative 9, we have negative 450. And then 30 times 10, which is 300. And then 25 times 1, we have 25. And then 11 times negative 4, we have negative 44. And then 45 times negative 9, we have negative 405. And then 7 times 11, we have 77 here. Now, we will multiply also the 3 rows by this second column here. So 5 times negative 5, we have negative 25. 24 times 4, we have positive 96. And then 15 times 0, we have 0 here. And then 10 times negative 1, negative 10. 5 times negative 3, we have negative 15. And 25 times 5, which is 125. So multiplying the second row by the second column, we have 80 times negative 5, we have negative 400. And then 89 times 4, we have positive 356. And then 85 times 0, we have 0. 84 times negative 1, we have negative 84. 82 times negative 3, we have negative 246. And then 90 times 5, we have 450 here. Also, the third row by the second column, we have 50 times negative 5, we have negative 250. 30 times 4, we have positive 120. And then 25 times 0, that's 0. 11 times negative 1, we have negative 11. And then 45 times negative 3, we have negative 135. And 7 times 5, we have 35 here. Also multiplying these 3 rows by the last column, the third column here. So 5 times 22, that is 110. And then 24 times 2, that's 48. And then 15 times negative 3, negative 45. 10 times negative 17, we have negative 170. And then 5 times 17, we have positive 85. And then 25 times negative 21, we have negative 525 here. And then the second row times the third column, we have 80 times 22, we have 1,760, added to 89 times 2, we have 178, and then 85 times negative 3, we have negative 255, and then 84 times negative 17, we have negative 1,428. And then 82 times 17, we have 1,394. And then 90 times negative 21, we have 1,890 here. And then multiplying the third row by the third column here, we have 50 times 22, that is 1,100. And then 30 times 2, that is 60. And then 25 times negative 3, that is negative 75. And then 11 times negative 17, we have negative 187. And then 45 times 17, we have 765. And then 7 times negative 21, we have negative 147. And then simplifying this sample covariance matrix S, we have 1/5 of this matrix. So if we add these 6 numbers here, that is equal to 400. And then adding also this one, we have 171. Also combining these 6 numbers here, that is negative 497. Also these 6 numbers, that is equal to 171. And this one also, this is 76. And this one, the sum is negative 241. And also this one, this is equal to negative 497. And this one is equal to negative 241. And if you combine also this one, this is 1516. So our sample covariance matrix is a scalar multiple of this one by 1/5. So this is equal to 80 because 400 times 1/5 is 80. And then 171 times 1/5, that is 34.2. And then negative 497 times 1/5, that is negative 99.4. And also 171 times 1/5, that is 34.2. And then 76 divided by 5, we have 15.2. And also negative 241 times 1/5, that is negative 48.2. Negative 497 times 1/5, that is negative 99.4 here. And then negative 241 times 1/5, that is negative 48.2. And 1516 times 1/5, that is 303.2. So this is now our sample covariance matrix. And we know that this is our first variable, the second variable, the third variable. And because this is a sample covariance matrix, the first row is our first variable, the second row is the second variable, and this one is also the third variable. So what does it mean? 80 is the covariance between the variable x sub 1 and itself. So that is S11, the covariance between the first variable and itself, while 34.2 is the covariance between the variable of x sub 2 and x sub 1. So we have here S12. That's the representation. And negative 99.4 is the covariance between the first variable and the third variable. So this is S13. 34.2 is the covariance between the second variable x sub 2 and the first variable. So this is S21. And 15.2 is the covariance between the variable x sub 2 and itself. So this is S22. The covariance between the third variable and the second variable. So this is S23 here. Negative 99.4 is the covariance between the third variable and the first variable. So this is S31. And this is the covariance between the third variable and the second variable. So this is S32. But 303.2 is the covariance between the third variable and itself. So this is S33. So this is now the general representation of the sample covariance matrix. And you notice that the main diagonal of the sample covariance matrix are the covariances between the variable and itself. So you can see here that the subscripts are the same. So we have S11, S22, S33. So these are covariances of variables and itself. And the covariance of any variable in itself is the variance of the variable. So we represent this sample covariance matrix, the main diagonal, as S sub 1 because that is the variance of the first variable, and this one here as S sub 2 because this is the variance of the second variable, and here this is the variance of the third variable. So this is the main diagonal of the sample covariance matrix. That's why the sample covariance matrix is sometimes called variance-covariance matrix. Because off diagonal, this is S12. This is S13, the covariance between the first variable and the third variable. But this one is S21, the covariance between the second variable and the first variable. And this one is the covariance between the second variable and the third variable, because this one is the covariance between the second variable and the second variable. So that's the variance of the second variable. So we have also here S31, because this is the covariance of the third variable and the first variable. This is the covariance between the third variable and the second variable here. So this is the general representation of a sample covariance matrix, wherein the main diagonal are the variances of the variables here. And you also notice that the upper diagonal here are just similar to the lower diagonal here of this sample covariance matrix. So this is 34.2. The covariance between the first variable and the second variable is just the same as the covariance between the second variable and the first variable. Also this one, this negative 99.4, is the sample covariance between the third variable and the first variable, which is the same as the sample covariance between the first variable and the third variable. So it's commutative here. So also this one, it's the sample covariance between the second variable and the third variable, which is the same as the sample covariance between the third variable and the second variable here. And this is a good place to stop. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.